Hey there, man, Alejandro, and welcome back for day 280 of me doing daily code challenge that reach 1 year's worth of Greek contributions here on GitHub. Today is from April 22nd, 2025. Without further ado, let's get straight into it. Okay, today we got LeetCode hard problem 2338. Count the number of ideal arrays. Okay, I'm not gonna freak out. Oh man, it's gonna be a while until we're out of the count questions, eh? Alright, you're given two integers n and max value, which are used to describe an ideal array. A zero-index integer array r of length n is considered ideal if the following conditions hold. Every r of I is the value from 1 to max value, 0 less or equal I less than n. Okay, well, first of all, max value better be n or greater. Every ri is divisible by r of I minus 1 for 0i. Okay, return the number of distinct ideal arrays of length n. Sounds like a DP problem, right? Like a 2D DP problem, which is how many numbers left and your current value and whatever the max value is, right? But that would be pseudo-polynomial. And yeah, you're not going to be able to do it this times this. Okay, so that's what's going to make this LeetCode hard, right? The answer, yeah, okay. So here we can just do mod is equal to power of 10 to the 9 plus 7. Right, here, like, okay, dp, self, I'll take an index I, left, curve out, right? Here we'll say if num left is equal to 0, length of range of curve val all the way up to self dot max value plus 1. Self dot max value equals max value. Yeah. Return self.dp, it'll be num left is n. I guess we should say n minus 1 values left and 1. Or here we could say yeah, this is actually going to be way too slow. We'll just say for start num in range max value will equal self.dp of n minus 1 nums left and start num. Return res modulo mods. Yeah. To do, so add modulo here. You can probably add, yeah, I'm very bad with modular arithmetic. Honestly, one thing I wish I did in school was take a number theory course. That would have been very, very, very useful for sure. Okay, so for now we're going to build a solution that is obviously too slow, but at least might be correct. Also, let me put my computer to charge. That will definitely be something that is pretty darn important, so that my computer does not die on me while I do this recording. There we go. We can even increase the brightness a little bit. There we go. Okay. Okay. Here we'll do that. I is divisible by this, yeah. For next num in range, start num plus start num all the way up to self dot max value plus 1 by a multiple of actually this should be the current value, current num pretty much, right? We'll just say self.mod is equal to mod. Mass plus or equal to self.dp of num left minus 1 next num return less. Right, something like this. First of all, let's just run this. Yep, that would make a lot of sense. Wrong answer. Okay. Right. Should only include everything once, eh? It's blind. Rise. Okay. This 12 and this is 0. Wow. Distinct ideal arrays. Right, there'll just be no more numbers though, right? You need an array of length n. Interesting. Okay. start num1, 2 and 5. Value 1 is 5 arrays when it says 10. That should work. Right. 1 plus 1 is 2, and I'm going off by an offset of 1 each time. That's fine. It's giving me 10 though, which is interesting. Num left minus 1. Maybe what I should do here is just return 1. So I'm at 5. This guy gives me 4. Actually, we might not even do that. We'll just say yeah, we can. Assert current num. Num left greater or equal to 0. Assert this. Okay. Should we count? Times 2. Alright, so 2, 3, 4, 5. 2, 3, 4, 5. Oh, 1, 1 is allowed? Ah, 1, 1 is allowed. Interesting. Okay, so this would make sense. Yeah, so that's 5. Oh, now we're 1 off. Okay, so 1 has 5, 2 has 2, 2 and 4. 3 has 1, 4 has 1. We just don't have 5. Probably because we're not including max value itself. Okay, so that's perfect. Okay, so now let's submit something like this and assume we're going to TLE. Just out of the box. Yeah, so we TLE. Sweet. So we have a correct solution that TLEs. Great. Yeah, so here let me just do something like let me grab this value. Let's open up a terminal script. Yeah, so let me just Python 3 here. Oh yeah, I'm doing a hackathon video here. This over 2, we'll grab that value. Right, and we'll grab whatever this value, and I just divide this guy by 2. Alright, 14, 15. Maybe it's still too slow. Okay, no worries. Let's make this 1,000, and let's make this 500. Okay, that takes a really long time, but now we have something to. Okay, first of all, we're not gonna print stuff. So prints become hashtag prints. Okay, that just made things longer for some reason. Of course, we can get rid of this. Here, can I do a modulo mod here? Okay. Modulo self-demo. Self-demo. Modulo mod. Equals res plus this thing modulo mod. Nice. So it does help a little bit. Mod is equal to self.mod. Okay. Res plus count modulo mod. Okay. And one thing we can also do is get rid of this. Get rid of this. First of all, okay, so I expect something like this to be unbelievably slow now and not feasible. Of course. Now we're going to put a cache decorator and see how this guy behaves. Okay, so it's a little bit faster with a cache decorator. So there we go. We might as well try, and there we go. Okay, so we have a working DP solution. That's cool. We might as well make this just self.mods. That's fine. I don't mind. There we go. All right. So, looping through an up to max value is definitely legal because this is up to 10 to the 4. Right? But somehow, okay, so there's going to be some, either we need to do this in linear time or like n log n time. So this is going to be interesting, right? If we loop through max value, we got to make everything log n or constant time. If we loop through all n, we need to make everything log n or constant time. Oh boy. Something like this is a no-no because it'll be 10 to the 4 times 10 to the 4. Even though this goes, yeah. Interesting. Yeah, this is gonna be an interesting problem, right? So yeah, so DP obviously works, but it's too slow. So how are we going to? There's gonna be something sus about, like, numbers must be divisible. There's only so many options that you can possibly have, right? There's gonna be one of those where it's like I said, this to 1. First of all, this is times 2. No. Oh gosh. Yeah, no, we need the current number itself, that's for sure. Just the first one, okay. Because I'm trying to think of something like this. This is interesting. This is quite interesting, actually. Okay. Are there any hints for this problem? Because we do need them. Yes, there are. Acceptance rate 28.5%. Okay, I shouldn't waste too much time on this problem. That is kind of insane. Okay. Okay, so the OVN or event login way is probably gonna be cracked to some way. I'm starting to wonder, right? It could be something where it's like logarithmic, but in similar to spirit, something like the Sieva-Verratos-Denys for finding prime numbers, right? Where it's like you start off the square, you loop through by the number, so it ends up being like, logarithmic by like the both, like log n because of both ways. Well, n log n, n log n type thing. Okay. It's kind of nutty. To the 1 is 10. To the 2 is 100. To the 3 is 1,000. To the 4 is 10,000, yeah. Yeah, interesting, right? I might as well keep that there because I've made so many mistakes in the past. where it's just like I forget the module at the end, and that was the thing. And so it's just like I'm just like, yeah, even though that last module is useless, I'm just gonna keep it there for my own sanity, so I don't ever come across that bug again. How am I gonna make this faster? I don't want to look at the hints this early on. But yeah, it's pretty discouraging to see such a low acceptance rate, right? And I'm at a point where it's like I've solved the problem, but then it's like, how the heck am I gonna make this linear or n log n in terms of one or both of the inputs? I feel like, something like max value being linear is to just allow for, like, that being a starting possibility for every single starting number. Maybe something like this is on the right track. And then it's gonna be logarithmic. Yeah, it's not even O1 work here. Yeah, okay. I'm gonna end up looking at one of the hints. The acceptance rate is so discouragingly low that I want to make sure that I don't spend an infinite amount of time thinking about this problem. I don't feel too guilty just because we have, like, a correctly working solution. It's just obviously TLEs because, like, the asymptotic complexity is just way too bad on this one. So you know what? Without further ado, we're gonna get started with looking at hint number 1. Notice that an ideal array is non-decreasing. Ooh. That means, well, okay, yeah, increasing, obviously. That is completely obvious. Okay, consider an alternative problem. When an ideal array must also be strictly increasing, yes, I can indeed use DP. That is exactly what I did. Hint number 3. Okay. Combinatorics, really? Yeah, it's gonna be annoying. Okay. So what's annoying is about the alternative problem. Okay, if we want strictly increasing arrays, let me do something like this, right? So here we get 5. How many of them are strictly increasing? Not. 1, 2, 3, 4, 5. Good. I got 5, right? Here I got 0. Not strictly increasing, not, right? There. Wow. Okay, that is completely interesting, right? 0, eh? So with DP, it seems, interesting. Not quite. Interesting. When you specify strictly increasing arrays, You get something like 0 here. That is very interesting. Also, something like this, which is in the Sierra Elasticenis, is not going to work here. Let me just see. Here we actually get a bigger result. What the hell? Oh, because a 1 squared is... Yeah, okay. Well. Right. There's something like max of... Interesting. For now, we'll just keep it simple, where we'll do something like this. So this is very interesting. So what makes things slow is the fact that it can have the same number with itself. So it's like one possibility is something like num left here, right? Because however many numbers you have left, you can pick kernum and that each time, right? No, not quite. Yeah, this is what we need, right? Yeah, but this is exactly the problem. Yeah. Yeah. So it's like all the ones, or you pick a 2 and have all the 2s. Not quite. Yeah. Okay. Yes, it turns out this invariant is a lot faster to solve for. Right, we go from 700 ms to 4 ms. Very interesting. Remove caching, we might even go faster. Yeah. Damn, if only they didn't make it that way. Now how do you use combinatorics? I'm so bad at combinatorics. What can we do? We need like 1, and you can pick. Yeah, this is so annoying. I'm actually not sure. Okay, I'm gonna look in the discussions to see if there's like that actually useful hints guy, because I can't think of how I'm gonna do this with combinatorics. When I saw this, took me 1.5 days. Quite hard. Yeah. Okay, I could do that. Count again. Here we go. Yep, there's just people complaining. Counting. Yeah, I feel this. Oh, there is a CFOS thing here. Okay. But no actually useful hints guy. That hurts. That hurts. Yeah, how do you... Okay, not really helpful. What's LeetCode 1735? Let's see what this is. Keywords to make array with product. You're given a 2D integer array queries for queries of I. You can place positive integers. Hello, Osmani.
Hello.
You place positive integers into array of size and I. This is
counting problem?
this is the problem.
Oh shit.
Yeah.
Nice. You were blessed with a hard counting problem.
So look at this.
Thank God you already know segment.
So look at this.
Yes.
I have a working solution. It's just too slow. And I looked at the hints, and the hint says use combinatorics, my friend. And I'm like, I suck at combinatorics. That's literally the hint. Yeah, TLE. It's like
5 out of 40.
Well, so okay, so if I don't include for
Have
the
you tried caching? I'm joking.
yeah, right here. So kernum, bro, you see 659? If I do this plus kernum, I go from insanely slow to mwah level speed. Okay?
Yeah, because it
But-
doesn't work.
No. Because here's
It
like
fails right there.
Okay. It wants you to do r of I is a value from 1 to max value. R of I is divisible by the previous number. But a number is divisible by itself, which is so annoying. And because of that, that makes things giga slow. So for example, 1 is valid. 1 is a number between 1 and max value, and 1 is divisible by 1. And so it's just like, ah! And they're
So
saying,
how does that relate
so
to adding
so you see how this is
itself?
super fast? They're like, okay, so if you don't do that, wait to TLE. If you do that, super fast and wrong, Use combinatorics to jump the gap between the two worlds.
Well, I still don't understand. So
Read the
when
problem.
you add the I see. We've been indulging in some sugar. I guess this is stressing the fuck out of me.
A little bit. Okay, and now there's another LeetCode hard that someone says is easier to solve, so let me
this
check.
was the pizza stuff we bought?
Oh shoot, I didn't put that in the trash.
No, but what is this?
Yes, it is. I ate 4.
It's like mini pizzas?
I ate 4.
Really?
Yeah.
I'm hungry. Maybe I'll make one. Is it good?
Yeah. You should. Get the pepperoni, it's better.
Okay.
But it's not capital.
Is it in the oven or in the microwave?
Microwave, 1 minute 30 seconds.
Not too soggy?
A little soggy.
Oh, okay. No.
Well, like you'll see, it's not soggy like how you think of a soggy pizza. It's in a good way.
Okay.
Oh, wait. Find the number of different ways you can place the product of the integers is k. Two 6. There are 4 ways to fill an array of size 2. Multiply the 6. 1 6 2 3 3 2 6 1. Oh, interesting. Okay. So yeah, so this is very similar in the same way of num left and go product. Product left, I could say. Yeah. Right, like here what I can do is, yeah, I could add an extra parameter for n, k in queries. Mod is equal to power of 10 to the 9 plus 7. Res equals res plus something. Modulo mod return res. And just because I'm paranoid, here we'll say.
You made some damage.
Actually. Map. Here we'll say an array of mods. Left equals 0. Product left equals 1. Okay. Here we'll say here we should get the prime factors of a number. True, return false, something like this. One, one, one. Count is equal to 0. of say count. Okay.
How much time did you put it in the microwave?
130.
Yeah. 50 seconds. Oh, it's not that big.
Okay, there we go. So like this, like this. So someone is saying to solve this problem because it's easier and similar, and I agree. Yeah, okay, I should have looked at the, yeah, so this is a TLE as well. So yeah, my method of approach, yeah. So this is a very similar problem that has a higher acceptance rate. I definitely could optimize this by only considering valid products. I guess this is gonna be another one where if I change this to a 2, it's also gonna be super fast. Yeah, it's gonna be, so yeah, so let me take something like this guy that I TLE on, and now if I put in a 2, it's gonna be like super fast. Or reasonably fast. Yeah, but if I do a 1, it's just, okay. Should also figure out how, like, yeah. Something like this is like, how do you get the divisors of a number? So, prime factorize ki and count how many ways you can distribute the primes among the ni positions. After prime factorizing ki, was there x amount of prime factor? There x plus 1 less. Oh my gosh. Yeah, that's insane. After prime factorizing ki, I suppose there are prime factors. Yeah, here we could just do a def cache, def get prime factors, man. Return. Is 1 prime? I guess not. For these cases, yeah.
This one is prime.
I always remember that I thought 1 is prime because it's only divisible by 1 in itself. But I remember in high school it was like, no, 1 is not prime by definition, blah, blah, blah.
It is prime.
I mean, you can Google it, but...
It's 1, 3, 5.
Those are odd numbers.
1 is prime. 2 is prime.
Yeah.
3 is prime. 5 is prime.
You said 1, 3, 5, you skipped 2.
Yeah.
So I thought you were just saying odd numbers. Is 1 prime?
I guess not. And then it's 2, 3, 5. Yeah. 2, 3, 5, 7.
Yeah. It should be in my opinion.
2, 3, 5, 7, 11, 13.
Bro's got it. Bro can solve the LeetCode problem.
Yeah, just do it if else.
You know there's actually an efficient way to compute all the primes up to n.
Mm-hmm.
It's with the Siever Veratos Dennis. Actually, I should get
I know what I need. I know what we need.
What?
A shake.
I don't want to build a Sieverretosthenes here. Just to solve a hard that's not even related. Okay, I should do it. I always forget how to build a Siev. So it'll be Siev is equal to everything is true up to xk plus 1 to false, Siev of 1 is equal to false. Alright, what's the maximum k? Yeah, it's up to 10 to the 4, that's completely fine. Now for something like this, we shall say otherwise it's prime. So say prime to the power of 2 max k plus 1 factor of prime, so Siev of non-prime, false. F string. Here I'll just say primes is equal to in range length of Siev is Siev of I. Siev and now print f string primes equals, let's see if I did the Sieverretosthenes correctly.
Nice.
Yay. By the way, so this algorithm computes, so if you give me a number n, I compute the first, all the primes up to n inclusive in O of n log n time. That's what the Sieverretosthenes helps me do.
That's insane.
That's I remember I was doing one of the LeetCode contests, and a guy commented like, "Yo, for prime problems, you should learn the Sieverretosthenes." I was like, "What is this magical being, deity?" And it turns out it is extremely useful in LeetCode problems that are like, "You will do math now." It's log. Yeah, it's cool. Here we should
It's cool. It's basically like it's basically all of n.
Yes.
Of n log n.
Now the only problem is that like n can be a huge number, right? If you want all the primes up to some huge number, the only thing is I create a Boolean array that is of that number, so it's really annoying, right? It only requires log n bits to store a number, but like if I need O of n space, that's pretty bad. So that's the huge downside to the Sieverretosthenes is you need O of n space, which is huge sometimes.
Every time.
To get basically
because it pretty much uses the
you want the
previous
you want
to
the
get
first
next.
n primes, right? The first number, all the numbers that are prime up to n, what it'll do is you create a Boolean array of all the numbers up to n. And for each of them, you either store false or true, depending on if it's prime. So here's like, I create an array of length n, where it's all trues. And then the way it works is essentially it's like, okay, 2 is prime. So start from 4, 6, 8, 10, 12, 14, those are all not prime. All multiples of 2 are not prime. Mark them all not prime. Therefore 3, do 3 squared, which is 9. So 9 is not prime. And neither is 9 plus 3, which is 12, plus 3, which is 15, plus 3, and so on. And so the reason it's n log n is because for the next prime you take, like 3, you square it, so that becomes 9, and you go by a factor of 3 as you go. So it's like the fact that you go by the factor of a number, and the second, which is that you square the number, makes it log in both directions. So it's an n log n algorithm. But it's pretty damn, I would not want to prove that. FCF prime. Oh gosh. Okay, so I've got all the primes. Yeah, 2, 3, 5, 7, 11, 13, 17. Yeah, so that's good. That's crazy. I have gotten better at LeetCode, that is for sure.
Can't believe you implemented that so quickly.
Yeah. Practice.
Although it doesn't sound that hard.
Yeah, I guess not. Like, this is the code for this. You have of Eratosthenes. I hope I spelled that right. You could actually understand it.
Yeah.
I marked them all as prime, true, up to like that number plus 1. 0 is not a prime number. 1 is not a prime number. All right. For each prime in the range 2 all the way up to that number. If it's not prime, ignore it. If it is prime, go from, I don't know why you should get to square. It's because apparently the previous one has done enough work to check all the primes from that point. Like, I thought you would start from, like, you know, the prime times 2, not the prime squared. But I guess it works. Trust in the algorithm gods. All up to the number itself, and go by a factor of prime each time, and mark them all as false. And there you go. Yeah, it's algorithm a kindergartner can understand. And then the primes will just be all the ones that are still marked true. You mark everything that wasn't prime false. So whatever lived are the primes. Okay, sweet. So
Remember when I didn't know how to code? Didn't know what a variable was, what a for loop was. It's crazy. Now it's more about thinking algorithmically and like what time complexity this shit is. Nothing related to syntax.
yeah. Otherwise, or here I should say if n modulo prime equals 0. And then here I'll just say prime index plus or equal to 1 loop invariant. There we go. Okay, sweet. So something like this. For divisor in self.get prime factors product left
Antibiotics are useless. Probiotics don't work. Genuine hand. At lunch.
Let's see.
Conspiracy theory style. Oh, there it is. When you're done, I'll make a smoothie. For both of us.
This is interesting. I'm not even solving the original LeetCode problem at this
Yeah,
point.
but that one's pretty cool.
Actually, wait. Yeah, this is not the approach that I want to go through things. Yeah. How many ways you can distribute the primes? Two and six, eh? Interesting. Actually, we should just fill things with ones at the end. Yeah, we can fill things with ones. Oh, that's gonna be so cool. That's actually so cool. That's so cool. Okay, yeah. So what we need to do is, how do you do n choose k? Help math. Is there import combinatorics or help math? Import math. Help math. Permutations. Oh wait, this is actually good. Is there combinations as well? without order. Oh, I see. So it's n over k factorial times n minus k factorial. What about permutations? So it's combinations, you just add a k factorial. So math that perm. Yeah. Yep. This makes sense. Def query solver self n comma k print f string self dot query solver n comma k equals okay. We're gonna say we're gonna get prime factors. D is equal to this. Here we'll say d dot values factor count factors is larger than n. Return false. Otherwise, insert 1 not in D. Count factors less than n. Count factors don't have enough factors. A bunch of ones. Okay. And then so here we'll say yeah, man, I suck at combinatorics. So it's like now we have a dictionary. It's like, you know, I have 3 2s, this, that. It's like how many orderings can you create with them? Is it the number of numbers factorial divided by each of their frequencies?
Do you know which one is my laptop
And this one?
Is the one you're using?
Yeah, you can feel free to use it,
You,
or you want to use one of mine.
Charged? I don't mind using
Here,
yours.
this is mine if you want to use it, and it'll be faster because it's a big block. Numerator. Something like this. It's equal to, is that correct? No, right? D equals. So how many ways to multiply to 6 with 2 numbers? See, 1 and 6. Maybe the answer should always be +2. Right? 6 with a bunch of 1s. 1 with a bunch of 6s. So it'll always be the number followed by a bunch of 1s. So it'll be, and choose the number. Oh my gosh. Case 1. N minus 1 once. There are case 1 will be, there's n spots to choose one, right? If I do math.combination of 5 choose 1, yeah, it's 5. Combination of n choose 1, right? Or if I do n is equal to 5, right? If I do this, if I do n minus 1, n, choose where to put the n minus 1 ones, right? It's the same, right? Even if I make n something crazy like this, n, yeah, it's the same, right? Assert case 1 is equal to n. Case 2, use all the prime factors. What if a number is prime? All right. There you go. That's bad. Yeah, well, k equals 1 is kind of an annoying case. Math out. Yeah, 120. Divide by each of the frequencies though. Something like this is interesting. Really no. Oh my gosh. What is this number? $660. 660. 2 divided by 2 divided by 3 divided by 5. 11.
When you're fishing, you don't go to the fish. You let the fish come to you.
I see. Are you good with combinatorics?
Pathetic.
Oh,
I
God.
cannot believe you're giving up on yourself. Come on, man. You got this.
No, there's a bug I can't figure out.
A bug?
Like I feel like I'm not doing combinatorics properly. Like the way is like okay, for example, a number like 660.
Yes. 616?
660.
Okay.
Right? The prime factors are 2, 2, 3, 5, 11. If I do 2 times 2, that's 4 times 3 times 5 times 11, right? These are the numbers that multiply to 660.
I see. You
So-
have to find the prime factors and multiply to a certain number.
No. So what I need to do is like, I'm given n numbers.
Mm-hmm.
How many sequences of n numbers can I create?
Mm-hmm.
Unless it's asking for combinations, not permutations. But how many sequences of n numbers can I create where the product is 660? And I'm given 73 numbers.
Okay.
So how many permutations of 73 numbers can I create that multiply to 68?
Can you check if he's asking for combinations and not permutations?
All right. Well, like,
'Cause
I'm just
what's
asking.
the difference? The difference is in permutations. No, in combinations, the order matters, right? That's the only thing that matters.
Oh,
Like, that's the
oh
only thing
no,
that
no, no.
changes.
I just realized it's not just all this and then multiply by a bunch of ones. I could also have this 2 and 2. I could merge it into 1, make 4, and
Mhm.
multiply by that by 1.
Yeah.
Oh, that's so annoying.
No. That's very simple too, right?
Alright.
No, okay, sure, but like when you realize this, you're realizing that you could also combine the same numbers that you have, right?
Oh, this is so annoying. Okay, let me see. After
Like,
prime
it's
factor
not
is
just 2, it's
included,
2
there are x
squared.
amount of prime factor. There are x plus n minus 1. Choose n minus 1 ways to distribute the x prime factors. Allowing repetitions.
Yeah, never thought about combinatorics when it came to LeetCode. Damn, I got a long way to go.
Okay. Equals length of d. Turn. Yeah, it's just wrong. What the hell? Yeah, that's gonna be my problem. I can combine primes. Okay. What's the discussions for this one? Yeah, this is kind of nuts. And this isn't even the actual daily I need to solve. Holy crap. Okay. Wow. Yeah, okay, I'm at a point where I just want to see the prime factorization part, right? Oh, but there's no editorial. Oh my gosh. Yeah, but the primes, there might be. Okay, I need to see a solution for this problem. Yeah, I need to see this. Yeah, only once prime factorizes. Oh, I see. First prime factor, second prime factor, third prime factor. Wait, what is this? Okay. So the A1s do not come anywhere. Right? It's not the values themselves. Doesn't seem to be permutations. heck? Oh. Let me do import functools.reduce. Equals functools. Help functools.reduce function. The x comma y, x times y. Equals map. The x the get prime factors of k. Let's do list. Still no. This should be math.com. Still no. Ooh. So it is about their frequencies. Okay. Something like this. Okay, so we have a working solution for that one. That's cool. So we are able to solve problem 1735 only thanks to that magical combinatorics formula. So if that's an easier problem, then screw me, man. Cause yeah, I don't get this formula at all. It's just yeah, I'm so terrible at combinatorics. It's kind of crazy. I see, yeah. Yeah, I mean that's just something crazy, right? We can at least copy our own Sieva Veratosthenes thing. Nice. That's unfortunate. No. What does matter is those prime factors values. So we should definitely do that. Yeah, I like the else statement more. Yeah, DP is kind of useless here. Maybe we'll get rid of the cache. Okay. Right. Modulo mod. Does that work? Does indeed work. Modular arithmetic, very interesting stuff. Nines. If I put a cache decorator here. Oh well, it does make things a lot faster. Okay, well, that's my solution to this one, but that's not the actual daily problem, sorry. If that's an easier version of this problem, then I am cooked, ladies and gentlemen. I'm absolutely cooked. Okay, one thing is... Okay, I'm gonna refresh this page and see, are there more discussions now? Yes, there's 34. I will sort by newest. Yep. I mean, we're just getting complainers. Bless you, money. Yeah. Yeah, okay. What is this? Hard question. The crucial fact is for any number x with prime factor. Oh, wait, okay. Well, what was this problem again? You're given. Yeah, I'm so I'm so used to solving this problem over here now, that my mind is just on this problem, that I completely forgot what I was originally solving over here, because this was supposed to be an easier hard to solve than this one. Holy crap. Okay. You're given two integers and a max value, which are used to describe an ideal array. Provide the value from 1 to that, so you're using dp. I mean, yeah, just in case I have a def as cf self and takes a number n. Turn cf. Eratosthenes. Max k. And here I'll just say if cf of prime I think it's more readable like this. Okay. Yeah, I don't know if we necessarily want. Yeah. And then wait, could we use this as a helper? No. Yeah, it's not gonna be a product of something. It's just things that are divisible. Unless, no. Okay, yeah. Yeah, I remember what we were doing. Okay, what was that comment again? For any number x with prime factorization, the number of arrays of length n ending in x is equal to this crazy formula. Okay, so this is going to be a huge hint that we use. Okay. Hint from the discussions. I'll put this in like this. Holy crap, okay. For any number x with prime factorization is equal to p underscore 0 e underscore 0 times dot times p of this factorization k minus 1 Number of arrays of length n ending in x is equal to C of n minus 1 plus E0 times times C of n minus 1 plus, okay, yeah, this is a combinatorics problem. I suck at combinatorics, so yeah, this is just like getting good at combinatorics is something that takes like an unbelievably ridiculous amount of practice in the field. Like, it's not something that you just build as a nice little skill on the side, right? Like, for example, I was struggling on segment trees problems because I didn't know what a segment tree was. Yesterday, I spent an hour learning what a segment tree was from LeetCode videos. I spent 30 more minutes, like, implementing one of my own. Then I'm like, okay, I could do this with a function and so on. Once I get a segment tree problem, I'll know how to apply it, right? Getting good at combinatorics, it's like one of those things where for some people it's more intuitive than others, but like in the average case, it's like, not the most intuitive thing in the world for most people. You need an unbelievable amount of practice. I had a full semester at a university of me working on combinatorics problems, and that was not enough for me to even get good at this. So, yeah, I understand why people love it. I just do not personally do myself. So, yeah. Okay, so using that, so for any number x with prime factorization, the number of arrays of length n ending in x is equal to okay. Using above hint, number in range 1, max value. And then is of length n ending x via above formula. There we go. That's all I'm gonna do. Okay. So yeah. For x in range 1, max value plus 1. Here we're gonna say yeah, so here def get prime factors. Oh, do we really have to build NCFs? No, there's no way. No, this is all the prime numbers. Yeah, all the prime numbers up to max value. Let's not make this a function. Step 1, CF use to find all prime numbers less or equal to max value. As equal to max value. String primes equals. Let's just make sure we do that correctly. Okay. Okay, I'm gonna comment this all out. And now it's gonna tell me it's about this. Of course. 2, 3, 4, 5. Yeah, 2, 3. 4 is terrible, actually. Wait, what the heck? Really now? What the heck is the difference? CIV equals true times max value plus 1. Okay. Oh, if not, oh my gosh. So dumb. 2, 3, 5, 6. Yeah, oh my gosh, that's so. Yep, yeah, I remember making the mistake. Also, let me increase my brightness. Here I'm just gonna copy my own get prime factors function. There we go. That'll be useful. X. Okay. It's equal to Cn minus 1. Yeah, let's go see the. It's just gonna be something like this. or we'll just keep it in terms of his formula. E. Oh no, network error, really? Come on. Is your Wi-Fi down? I can't refresh my page. Okay, it's back up. Two, 4, 6. Okay. Max value plus 1 actually. Include max value. 4, 6, 8. Frick. Sum of res. Sort false. One alert. Append 1. Modulo mods. Wow, so that worked. Let's see. There we go. Completion streak 280 days. Consistency is key. See you tomorrow. Jeez, okay. Well, thank goodness for that guy in the comments. My goodness. Yeah, here let me just say. Only combination is to pick the value x for all n elements in the array. This is valid for is divisible x for any x. And here we'll say res is equal to 0. Res is equal to res plus this modulo mod. return res. Res plus or equal to 1. Okay, this might be a little faster. All right, yeah, well, here we're gonna do some optimizations. First of all, do we need the cache? Let's see. Not really. Yeah, it doesn't really make a difference. Mod. Otherwise, is equal to this. Res plus count modulo mods. Is this a little faster? Doesn't really matter at the end, yeah. Okay, all right, final solution. Here we go. Okay, yeah, we're stuck at the 800 ms range, so on. I guess some people did this a little faster. 0 ms, that is crazy. Okay, I mean, that is what it is, right? Yeah, maybe this is a little computationally exhaustive, right? Coms is equal to for e and prime factors dot values. Right, this might be a little faster. Not really, to be honest. Yeah, none of this actually makes a difference. Okay. Okay, I mean, all right, there we go. That's pretty much it. Okay, so nevertheless, as always in all my videos, I do a quick recap if I ever tell the promise for this one. Essentially, we want to count the number of ideal arrays. An array is ideal if it has n elements, and all those n elements are numbers between 1 and max value, which is max value passed into us. So we must count the number of valid arrays of length n, where every number is between 1 and max value. It must be that for every index I, r of I is divisible by the previous number at r of index I minus 1. Now, a small caveat is to denote that a number is divisible by itself. For example, 5 is considered divisible by 5, okay? And return the answer to the modulo 10 to the 9 plus 7, yada, yada, yada. Okay, so I first, at the very beginning of this problem, I wrote a DP solution that worked but was too slow. And I got stuck in terms of how to actually solve the problem. And so what I ended up doing is I ended up opening all of these hints, and I got stuck again on the DP thing and combinatorics parts, where I was like, okay, I noticed that like if you don't consider like, you know, starting from the same number itself in my DP function, it was way faster but incorrect, and I didn't know how to use combinatorics to bridge the gap between the solution that was too slow but correct and the solution that was fast enough but incorrect, right? So I ended up looking at the discussions, and through the discussions, someone said to solve this problem, which was a little bit a simpler version of this one. I did end up solving this LeetCode hard, but only after I looked at the solutions and the hints to essentially figure out, like, how to do the combinatorics part, right? I got everything done inside of this question except the combinatorics part, which included Sieva Veratus Tenis over here, get prime factors, yada, yada, yada. Except for the combinatorics part where it got a little bit confused, and this combinatorics part actually happens to be the very same thing that we end up doing in the other problem. Don't have to worry about what this problem is. I just ended up solving it as part of my solution to this one, just because one of the discussions recommended it. Then finally, I came back to this problem, and I'm like, okay, I still have no idea what I'm going to do combinatorics-wise. And I found this beautiful, beautiful comment. Where is it? Let's do by newest to oldest. Yeah, this one. Beautiful. And when dang. I hope I'm saying that correctly. I'm gonna put a thank you so much. Couldn't have solved it without this. There we go. Beautiful. Okay, so hard question. The very crucial fact is for any number x with prime factorization, where it's like, okay, p of 0 is the first prime, p of 1 is the second prime, p of k minus 1 is the kth prime, where the exponent is essentially, it's like, okay, like, for example, a number like here, if I come on here, a number like 660, right? The prime factors are 2 times 2 times 3 times 5 times 11, right? These are the prime factors of 660, but here you'll notice that there's 2 primes, right? So here P0 would be equal to 2, with E0 being equal to 2 because there's 2 primes, so 2 squared, right? P1 would be something like 3, and E1 would be 1 because there's only 1 3, right? So 3 to the power 1 times 5 to the power 1 times 11 to the power 1, right? So that's kind of what's going on here. And it says, okay, like given, like, if so any number, by the way, is essentially a product of its prime factors, right? Which could be itself. And essentially, what to do? I suppose I could. Yeah, okay. Once you have the prime factors of a number x, all that there is left to do. Okay, now I'm confusing on something. Yeah, if something was its own prime factor, it should have been used. Okay. Anyways, I'm gonna discard that part for now. So if you have all the prime factors for a number x, where every single number has a list of prime factors, get the frequencies of each prime factor, and then this is the formula for computing how many ideal arrays of length n ending in x there are, right? And it'll be combinations of n minus 1 plus e0, where e0 is the first exponent, choose e0. Times c of n minus 1 plus e1, choose e1, times times choose n minus 1 plus ek minus 1, choose ek minus 1. Why, you ask? No idea. Okay, I saw this stack exchange and so on that kind of explained this HNR function and so on, and like why this is the one where you pick things and so on. If you understand this better, then let me know in the combinations below. I guess there's like a little bit of intuition here that I might get, but I don't fully understand, and I'm usually not that great with combinatorics. And combinatorics is one of those things where, again, it just takes a massive amount of experience to just get good at combinatorics. And like a lot of my friends from school, this was like one of their favorite subjects. Like they would always say like, oh, you want a bird course? And a bird course is like a super easy course. It's like, oh yeah, take Math C, whatever it was, which is like combinatorics. I looked at them like they were monsters, right? But like for math majors, they're like, oh, combinatorics, easiest thing in the world. For me, I hated combinatorics. It depressed me in my first semester of school in my discrete math class, where the first half of the semester was combinatorics, and I really did not enjoy that topic. I understand what it is. I understand a lot of the intuition behind it, but I was never good at it, nor did I ever seek to get good at it. I always saw it as kind of like an enemy type of thing. And I think it's different from something like, I said earlier in the video that yesterday I literally learned segment trees, and it was just like, I watched a 30-minute video from LeetCode, I processed what he was telling me, I ended up implementing my own, and not only like a summation segment tree, but like, a min/max segment tree and so on. And now I feel like, okay, if I get a problem that involves a segment tree, it's like, Okay, that's another data structure of my toolbox that I know how to use, know its purpose, right? Know where to use it whenever it's like, I need to do a range query and I need like, to abide by log n updates and ranges, which is the use case that I really want to use it for is essentially it's like if I want to ever find the min or max of a certain subarray of my current array, but in an efficient way, I know that I can't do that with prefix maxes and prefix mins. So like, I can use a segment tree for something like that, right? And so that's a very cool, powerful thing to learn. For something like combinatorics, it's just pure math and it just comes with a whole bunch of experience. And I'd much rather, learn other things than just waste all my time learning combinatorics just to be better at solving a few combinatorics related LeetCode problems. It's really just not part of my interest. So this formula, I'm just going to take it as black magic, but using this hint, problem becomes very simple. So now that we know that, okay, for any number x, with prime factorization this, the number of ideal arrays of length n ending in x is equal to the following formula. First things to notice is that max value is up to 10 to the 4. So we can go through every single value between 1 and max value. This is perfect. We can fix x, the ending x in our array, to each one of these max values, which will take 10 to the 4 worst case total iterations. And for each of them, we can compute in O of 1 time how many ideal arrays there are based off n, right? We're using this formula over here. What we need is for every single number x that we end with between 1 and max value, we need to get the prime factors and the frequency of that prime factor per number, right? So here, this is why I use the CF of Eratosthenes to find every single prime number between 2, which is the first prime number, and max value itself, right? Which is an O of n log n time. I'm not going to say why, I just know that time complexity off the top of my head. Essentially, the way it works is you create a Boolean array of size max value plus 1, where the index I inside of the CF will tell you if number I literally is a prime, right? True if it is, false if it isn't. Initially, you initialize everything to prime. You set 0 and 1 to false because they're not primes. And then you say, okay, for prime in range 2, comma max value plus 1. If the number is prime, then, okay, square that number and go through every single multiple of that prime, right? So it's like, for example, 3, you would say, okay, 3 is prime. Well, okay, 3 times 3 squared is 9. Then you say 9 is not prime. Then you'll say 9 plus 3, which is equal to 12, is not prime. Then you'll say 12 plus 3, which is equal to 15, is not prime. 18 is not prime. 21 is not prime. 24 is not prime. 27 is not prime. 30 is not prime. So the point is that the way the CF of Eratosthenes works is you initialize everything as prime, and then you go through all the prime numbers and those guys' multiples and set them as non-prime, right? For example, with 2, you'll clear out all the even numbers, right? You'll say 4 is not prime, 6 is not prime, 8 is not prime, 10 is not prime, so you'll clear out all the even numbers, right? For 3, you'll get rid of all the multiples of 3, right? So 9, 12, 15, 18, 21, etc., right? And you just do that for every single number all the way up to max value. I wonder actually here, can I go up to math.square root of max value? Math.ceil. Oh wait, you can do that with the CF actually, can't you? Ooh, that's cool. Well, it didn't bring my time complexity down by that much, but that's a very, very, very cool thing. And in fact, I could have done the same thing here for this problem over here, right? You will say max k. Okay, and we can solve this one a little bit faster too. Not by a huge amount, but like, a little bit. So there we go. Okay, I forget that about the CF of Eratosthenes. You only have to go up to the square root of the max number, and for each one of these, you'll square it, which is where the n log n comes from, right? The fact that you're going up to the square root here and the fact that you're squaring here is where you get those two merging logs. So you get n log n total time complexity, right? And also O of n space. Okay, but that's just the CF of Eratosthenes. It just gets us all the prime numbers that are less than or equal to max value, right? And here it's like, okay, prime is equal to each number in up to here I should say range max value plus 1 if CF of I, right? And something like this will also work, right? So there we go. So for every single number all the way up to max value plus 1, we will mark it as prime if it is prime, right? So here we get every single number all the way up to max value if CF of I, i.e. if it is prime, right? And then we'll just set that as self-dot primes. Okay, so now that we have that, we can essentially, given any single number, get all of its prime factors. How? We're going to set this to a default dict. We're going to say, okay, we're going to loop through all the primes that we need, right? So while this number is greater than 1, we're going to keep dividing by prime factors, right? So here we'll say, okay, let's get the current prime, which is starting from index 0. So self prime is at prime index. And okay, if n is divisible by the current prime, right? Here we'll actually say while n modulo prime is equal to 0, we're going to say, okay, let's keep dividing n by that prime number over and over and over and over and over, and every single time I divide by it, as long as it's still divisible by prime, I'm going to say, okay, it was divisible by this prime number one more time, right? So while it is divisible by prime, I'm going to keep dividing it by prime, and I'm going to keep track of the total numbers I divided by prime, right? And then at the very end, I will say, okay, prime index plus or equal to 1 to move on to the next prime, right? Whether I did some computations or not, I'm going to move on to the next index. And while n is still greater than 1, that means I still haven't found all the prime factors. So let me just keep dividing over and over and keeping track of the frequencies of each prime, right? And then I'll return prime factors, which will map all the primes that were actually the prime factors as the keys, and the values will be the number of times, right? So for something like 660 over here, this would look something like 2 2s, 3 would appear once, 5 would appear once, 11 would appear once, right? These would be the prime factors for the number 660. 2 2s, 1 3, 1 5, 1 11, right? That's kind of the idea. So this is just a little function, and I put a cache decorator here. It doesn't actually make much difference, so, you know, have it or not. I guess it's not that all that important. But here, otherwise, what I do is like, okay, since we know this magical little formula, right, that says like for any number x with prime factorization over here, the number of arrays ending of length n ending in x is equal to this magical formula that we can compute in constant time, right? Let me pull up the comment over here. Okay, so here's what we can do. We can fix x as the last number in our array, and we're going to do this for every single possible number, right? So for every single number from 1 to max value plus 1, we're going to fix x as that, we're going to fix that number as the last number in the array and say, okay, how many arrays can I have in total? So residence initial equals 0, and for each of these x's, we're going to compute how many there are total, right? So first things first, we need to get the prime factors of x, right? So we need to get x with prime factorization this, we need all the prime factors, which will map primes to their frequencies of the prime factors, right? Then, again, denote this formula will be the combination of n minus 1 plus e0, where e0 is the frequency of the first prime number, right? So what we're interested in is the frequencies of the prime factors. So here I do prime factors dot values to get their frequencies, right? And so our combinations will be math dot combination of n plus e minus 1. Or really just n minus 1 plus e to follow this guy's formula, n minus 1 plus e. Oh, is this just, oh yeah, I copied the formula from over here, but I guess it's the same thing at the end of the day, right? But we can do it the way that he did it, which is n minus 1 plus e, choose e, right? Yeah, at the end of the day, it's the same thing. Okay, so just to be consistent with that person's formula, right, it's just because I was using an equivalent form for this problem over here. That's not an issue though. But yeah, we're still at 772 ms. But the point is, I'm still following that person's formula over here to essentially solve this problem. So there we go. Math.comb of n minus 1 plus e comma e for e and prime factors of values. Beautiful. And the number of ideas arrays of length n is, yeah. So we follow this formula. So it's like, okay, let's get math combination of n minus 1 plus e comma e, right? So n minus 1 plus e, choose e. For each e in our prime factor values, right? So these exponents represent, like, you know, the frequency of each prime factor. So let's get all those prime factor frequencies. We'll label these e for each one, and we'll do, you know, math combination of n minus 1 plus e comma e, right? So these will be all the combinations of interest. Okay, if length of combinations equals 0, that means there were no prime factors, which is why I was confused, because like a number itself should be its own prime factor here. I guess it's like interesting, right? A number should be its own prime factor. So this is just an interesting case. Maybe it's like yeah, okay. Anyways, there are cases when length of the combinations is equal to 0, but when that happens, it's very, very simple, right? If length of combinations is equal to 0, that means, like, you know, it's not divisible by anything except itself, really, right? But the point is that we still have a number x, right? And now we just want every single, we just want a range of values from 1 to max value. Well, first of all, x is guaranteed to be between 1 max values, so don't have to worry about that. We need every ri to be divisible by ri minus 1. Okay, well, we are only allowed to have the number x here, but no problem. X is divisible by itself no matter what, right? So here, what we can do is say, okay, res, we're going to add one more combination. What is that combination? It's just going to be n of the value x all in a row, right? Because it satisfies everything. X is indeed in the range from 1 to max value, and every r of I is divisible by r of I minus 1, right? X is divisible by x, and since all of the values are x, then you always have that every single number is divisible by the number before it, right? X is always divisible by x. And that's the only thing, because there's no other prime factors, so you can only choose x, and so there you go, there's only one combination, right? Otherwise, if length of the combination is not equal 0, then we're going to do the thing. So here, remember, the formula says to take the product of all these values, right? Okay, so now I just have to refine this thing again. Newest to oldest. Right? It's to take the product of these things. So here I'm just using functools.reduce, which essentially takes take all numbers in an array and apply a function to it, right? So here I'm saying the function will be take two numbers and return to me the product of those two numbers, right? And apply it on comp. So I'm essentially going to take the product of all the numbers inside of combinations via reduce, and then I'm going to modulo that result by mod, right? Because again, the problem says if a number is too big, I return it to modulo 10 to the 9 plus 7, which is what I computed over here. So I'll just modulo it by mod, add that to res, right? So res plus record count, and again, modulo res by mod, just in case, just to keep things, small whenever I can. And then once I've done that for every single possible ending x from 1 to max value inclusive, then I essentially have all the counts that I need, and so then I can return res, and there you go, bada bing, bada boom. We have a reasonably efficient solution to this problem, and yeah, so there we go, finally done. This was quite the problem, right? I don't enjoy commutative over x too much, but this was an enjoyable problem, at least given the hint that I need in order to solve this problem, right? Knowing the intuition behind this would be kind of cool. So if one of you guys do know this, I would highly appreciate if you left a small little explanation down in the comments, and I will probably pin your comment if you end up doing that. But otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any way, shape, or form, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friends. Bye-bye.